This is session B7 on the Mach-Zehnder Interferometer. Last session was B6, the double slit experiment. If you have not watched that video yet, you should stop this video and go back and watch that one. That video includes information about wave functions, probability amplitudes, probabilities that you should view before doing this video. However, if you didn't like that video, you can continue with this video. It'll be fine. So in the double slit experiment, we saw that photons in a system that has two slits, the photons behave as if they could have gone through either slit, and that gives rise to constructive and destructive interference on a screen. And it's a very interesting experiment. Today we'll talk about the Mach-Zehnder Interferometer. It's a related optical effect with a different kind of setup. The Mach-Zehnder Interferometer is an optical experiment using mirrors and beam splitters, which are also beam recombiners. It has uses in classical optics, but we're going to look at it because this double path experiment can help us understand quantum mechanics. The results are similar to the two-slit diffraction experiment. You might find this simpler, but it's important to be exposed to both of them. Here's the setup for the Mach-Zehnder Interferometer. A collimated light source will come in from the lower left. It will hit beam splitter 1. We'll talk about this. Half of the beam intensity will reflect downward and take this bottom path, which will reflect off a mirror and come to beam splitter 2. But half of the intensity of the original light source will be transmitted through beam splitter 1. It'll be refracted because we're going from air to glass, and then it'll be refracted again when we go from glass to air, and it will take this top path, reflect off this mirror, and head at beam splitter 2. Both the top path and the bottom path will interact with beam splitter 2. Each will be split in two again, so that some of the intensity goes toward this top detector D0, and some of the intensity goes toward the bottom detector D1. But the light from the top and the bottom path will add or superimpose as they go through the beam splitter, and that'll give rise to very interesting effects, both classically and quantum mechanically, for photons. We'll talk more about this beam splitter. These beam splitters, they are a slab of glass, a rectangle of glass, with one side half silvered, either with silver or aluminum, some reflecting material, but half silvered, so it's not a complete mirror. Half the light goes through and half gets reflected. For this setup, it's important that the half silvered face be on the bottom on beam splitter 1 and on the top on beam splitter 2. We'll see that as we go further in the lecture. This experiment is carefully set up such that all of the light intensity will end up at the top detector, D0, and no light ends up at the bottom detector, D1. It's a little surprising that we can do this. In order to do it, the setup must account exactly for all changes in the phase of the electric wave or the wave function, as we'll see in this lecture. This is a possible time to take a break. The light source will be a collimated beam, a pencil beam of light that doesn't spread out. It could be white light, sunlight, or it could be a laser beam. The two mirrors reflect the light intensity completely, so there's no change to the classical intensity of light or to the quantum probability in the reflection. But the mirror inverts the sign of the electric field and the sign of the wave function. So it adds a phase of pi radians or 180 degrees. For a white light source, the experiment requires that the top and bottom air paths between the two beam splitters have identical lengths, so there's no relative phase shift that gets added between the two paths. This can be accomplished with careful adjustment, and it was done this way in the 1890s, where they used white light. If we can use laser light of a single color, it's sufficient for the top and the bottom path lengths to differ by any integral number of wavelengths, and that's easier to configure than the white light case. We'll use balanced beam splitters whose half-silvered surface splits the light intensity equally in half, and our beams will always be at 45 degrees from the perpendicular in the air. The light source hits beam splitter 1, whose half-silvered face is bottom facing. Half of the intensity will be reflected off the half-silvered face and take the bottom path. This is the air interface of the half-silvered face, and that reflection will have its phase be inverted in that reflection. So the electric field will be inverted, or the photon wave function will be negated. But half the intensity gets transmitted. When it does, the angle of the beam changes because of reflection. The refractive index of glass is higher than air. And then when it leaves the glass, the angle will be restored to its original, and it will take the top path. That transmission will not change the phase of the electric field or the wave function. The half-silvered face inverts the sign of the electric field and the wave function, so adding a phase of pi radians or 180 degrees, when the light beam reflects off the air interface of the half-silvered face, but not for transmission through the glass, nor reflection off the glass interface of the half-silvered face, which we'll see for beam splitter 2, not for beam splitter 1. Transit of the glass alters the phase, but we'll account for this in the final results, not the intermediate paths, so we can simplify the presentation and the math. But the final math will be correct. We're not cheating. This is a possible time to take a break. Let's look at this table that explains what happens at beam splitter 1. We'll have 3 columns to the table. The input, which comes from the lower left, the top output beam, and the bottom output beam. And we'll look at different quantities that are present at the input and how they change at the outputs. If the electric field amplitude was E, then each of the top and bottom outputs gets a lower electric field, E over square root of 2. But the amplitude will be the same because it's a balanced 50-50 beam splitter, but the electric field goes down by a factor of square root 2, so 1 over square root 2. Now the electric field has a sign or a phase, and that phase does not change for the transmission through beam splitter 1 that gives the top output. But the sign does get inverted for the reflection that gives the bottom output because that was the air interface of the half-silvered face. Now, the light intensity is proportional to the magnitude of the electric field squared at any point. So when the electric field gets divided by square root 2, the intensity gets divided by 2. So half the intensity took the top path, and half the intensity took the bottom path. For the wave function psi, or the probability amplitude, we'll take it as being 1 in the input, meaning there was a photon there, probability 1, 100%. But the top output and the bottom output paths, that wave function is going to get multiplied by 1 over square root 2. And the sign is going to be inverted and going from the input to the bottom output. Now the photon probability at a point is going to be the magnitude of the wave function psi squared. When we square 1, we get 1, which means there was a 100% probability of the photon being there. When we square 1 over square root 2, we get 1/2. And when we square minus 1 over square root 2, we get 1/2. So if we were to put a detector in the top path, it would have 50% chance of detecting a given photon. And if we put a detector in the bottom path, we would get 50% chance of detecting a given photon. But we're not going to put detectors in those paths. We're just going to work from the wave function psi. Now we're going to keep track of how many transits through the glass occur in different paths. The transmission to the top path had 1 transit of the glass, and the reflection to take the bottom path had no transits of the glass. And we'll keep track of this as we get to beam splitter 2. Now for beam splitter 2, it will help us if we look at the top path case separately from the bottom path. So here's the beam coming from the top path. It has been reflected off its mirror. It's going to hit the half-silvered face at the top, and half of its intensity will be reflected toward the top detector D0. But half of its intensity will be transmitted through the glass and arrive at bottom detector D1. Let's make a table to see how this works out. This is a possible time to take a break. So this table is what happens at beam splitter 2 from the top beam, and it has 3 columns: the top input, the top output to detectors D0 due to the top input, the bottom output to detector D1 due to the top path input. Now the electric field amplitude in the top path was E over square root 2, and that amplitude is going to get an additional factor of 1 over square root 2 as it gets split. So E over square root 2 times 1 over square root 2 is E over 2, and that is the electric field amplitude on the path to detector D0 and on the path to detector D1. Now, what was the phase or the sign of the electric field? It was positive after beam splitter 1, but then it reflected off a mirror, so it's negative coming into beam splitter 2. And that negative gets inverted again when it gets reflected off the half-silvered top face of beam splitter 2. So the sign or phase is positive heading toward detector D0, but it gets unchanged heading in the transmitted path to detector D1, so it's negative in the path to D1. Now, intensity in the top path was the square of the electric field, which was intensity over 2. So the intensity is proportional to the square of the electric field amplitude. The intensity was I over 2 in the top path. If we take E over 2 and square it, we will get an intensity of I over 4. If we take E over 2 and square it, we get I over 4. So indeed, in this case, the intensity got split equally in half in going to detector D0 and D1. The wave function psi was plus 1 over square root of 2 as it left beam splitter 1 on the top path, but it gets inverted to be minus 1 over square root of 2 when it reflects off the mirror. We have to multiply this wave function by a factor of 1 over square root of 2 in each of the output legs, and then we have to take into account the phase. The reflection that sends the beam to the top detector D0, that inverts the phase. So we get minus turning into plus, and 1 over square root of 2 turning into 1 over 2. The path to the bottom detector, D1, the phase does not change in that transition. So we get a wave function of minus 1 over 2. Now the photon probability is the magnitude of the wave function squared. So it was 1/2 in the top path. And when we take 1/2, the wave function psi being 1/2 on the way to detector D0 and square it, we get 1/4. When we take the wave function of minus 1/2 on the way to detector D1 and square it, we get 1/4. So the photon probability has split evenly in this case as well. Now the top path had experienced one transit through glass, and in its reflection on its way to the top output to detector D0, it does not transit the glass, so it still has experienced one transit. But on the path to the bottom detector D1, it passes through the glass, and so it picks up a second transit through the glass. This is a possible time to take a break. Now we'll look at the case of the bottom path being split by beam splitter 2. The half-silvered face is on the top, so the bottom path will transit the glass on its way to detector D0 and not experience a phase change. The bottom path will transit the glass, reflect off the half-silvered face, transit the glass again on its way to the bottom detector D1, but that reflection will not experience a phase change, a phase inversion, because it reflected off the glass side of the half-silvered face. Let's make a table of what beam splitter 2 does to the bottom beam. We have a column for the bottom input to beam splitter 2, a column for the top output to detector D0 from the bottom path, the bottom input, and a column from the bottom output to detector D1 from the bottom input, the bottom path. The electric field had been minus E over square root of 2. The electric field amplitude was E over square root of 2 in the bottom path. And this gets multiplied by 1 over square root of 2 to give an electric field amplitude of E over 2 for both heading to detector D0 and heading to detector D1. Now the electric field sign or phase, it had been negative after beam splitter 1, but after it reflects off its mirror, it becomes positive. And this sign does not change in going to detector D0, transmitted through the glass, nor on the way to D1, reflected off the glass side half-silvered mirror. Now the intensity is proportional to the electric field squared. The intensity was I over 2 in the bottom path. If we take E over 2 and square it, we will get I over 4. If we take E over 2 and square it, we will get I over 4. So indeed, in this case, the beam from the bottom path has split equally, split in half. The wave function psi, it had value minus 1 over square root of 2 in the bottom path, leaving beam splitter 1, but it gets negated after it reflects off its mirror. So it's entering beam splitter 2, its wave function is 1 over square root of 2. And when we multiply that by 1 over square root of 2, we get 1/2 for the wave function heading toward D0, detector D0 or detector D1, with no further phase change in either case. Now the photon probability is magnitude of psi squared, and it was 1/2 in the bottom path. And when we take 1/2 for the wave function heading toward D0 and square it, we get 1/4. When we take 1/2 as the wave function heading toward D1 and square it, we get 1/4. So the probability of detecting the photon split equally on its way to detector D0 and D1. The bottom path had no transits through the glass, but it experiences one transit of the glass in heading toward D0 and two transits of the glass heading toward detector D1. This is a possible time to take a break. Now we will see some interesting things. Let's look at the superpositions at detector D0 due to the sum of the top and bottom paths. So this is what our setup will look like. Top path is hitting beam splitter 2, bottom path is hitting beam splitter 2. Both of those paths split, so there's an electric field, an intensity, a probability, amplitude, and a probability heading toward D0, and a different electric field, intensity, probability, amplitude, and probability heading toward D1, and we want to see what those are. We will first look at D0 and then we will look at D1. So here's the output of the beam splitter 2 heading toward detector D0. We'll have three columns. The top output to detector D0 from the top path, which we've already worked out in another table. We have the top output to detector D0 from the bottom path, which we've already worked out. And we're going to combine them correctly in a correct linear superposition to determine what is the input to detector D0. Now, both the top path and the bottom path contributed an electric field amplitude of E/2 heading toward detector D0. And both had the same electric field sign or phase. So these two values add, and we get E for the electric field. When we take the intensity by squaring E, we get the original intensity of the original light beam, I. Now, notice that if we had just added the intensity, I/4 plus I/4, we would have gotten I/2, and that is not correct. We have to add the electric fields with the correct sign and then calculate the intensity. And we find that all the light intensity that we put in to beam splitter 1 goes to detector D0. This is a little surprising. Now let's look at the wave function. The wave function had value 1/2 heading toward D0 from the top path, and also 1/2 heading toward D0 from the bottom path, and they had the same sign, so they add and we get 1. And when we calculate the photon probability by squaring 1, we get 1, meaning that every photon that entered beam splitter 1 arrives at detector D0. Note that it would be wrong to just add the probabilities coming from the top path and the bottom path. That would say that 1/4 plus 1/4 is 1/2, but that is not what happens. We add the wave functions with their correct sign. In this case, they had the same sign. And then we calculate the photon probability from the wave function, and we get 1. Now, note that whether we took the top path or the bottom path, we experienced one transit through the glass for all the light going to detector D0. So all the light intensity and all the photons went to detector D0. This is surprising, but this is what we wanted to accomplish in the experiment. The top and bottom paths each had one transit of the glass through the beam splitters. This is a possible time to take a break. Now let's look at the superpositions at detector D1 due to the sum of the top and bottom paths. So we make a table of beam splitter 2 output to detector D1. We've already calculated the bottom output to detector D1 from the top path. I'm just going to repeat the column here. And the bottom output to detector D1 from the bottom path, going to repeat that column here. And we're going to have the new column, the linear superposition, that tells us the input to detector D1 due to the combination of the paths. The amplitude heading toward D1 from the top path, the amplitude of the electric field, is E over 2, and it's the same amplitude heading toward D1 from the bottom path, but they have opposite electric field signs or phases. So when we add them algebraically with their signs, we get minus E over 2 plus E over 2 equals 0. They have canceled. When we take the intensity as the square of the electric field, we get the intensity is 0. No light reaches detector 1, D1. Now let's look at the wave function. The wave function heading toward detector D1 was minus 1 over 2 due to the top path and plus 1 over 2 due to the bottom path. We add those and we get 0. 0 probability amplitude for a photon to be detected by detector D1. We then take that wave function and take its magnitude squared, and we get the photon probability, which is 0. 0 probability for a photon to be detected at D1. Now notice that it would have been wrong to just add the probabilities from the paths. We would have gotten 1/4 plus 1/4 equals 1/2, when the correct result is 0, by adding the wave functions, the probability amplitudes, with their correct sign. So we got 0. Whether we went through the top path or the bottom path, both paths experienced 2 transits through the glass on the way to detector D1. None of the light intensity and none of the photons went to detector D1. The top and bottom paths each had 2 transits of the glass of the beam splitters. The phases of the electric field and wave functions were in phase at detector D0 and out of phase at detector D1. It was okay for us to not show the phases at all the points within the top and bottom paths because of the following. Both paths had identical path lengths through the air. We constructed the experiment that way. Both paths had 1 mirror reflection. Both paths had 1 transit of the glass in the beam splitters in the path to detector D0 and 2 transits of the glass in the beam splitters in the path to detector D1. Both paths had 1 transmission through the beam splitter and 1 reflection from the air interface of the half-silvered face in the path to detector D0. However, the bottom path had one additional phase inversion at beam splitter 1 relative to the top path in the path to detector D1, which gives destructive interference or cancellation. So the electric field amplitude, the light intensity, the photon wave function, and the photon probability are all zero at the bottom detector D1 due to the phase inversion. Every single photon ends up detected by detector D0. No photons get detected by detector D1. This is a possible time to take a break. With this quantum mechanical wave function for the photon, interference is due to each photon interfering with itself due to the two paths, not due to a photon interfering with other photons. So we see the same probability distribution by accumulating individual photons slowly at the detector as for the intensity of a classical light beam traveling wave of electric and magnetic fields. We could think of this in two ways. Each photon is conveying the phase information that is present for the classical light beam sine waves of electric and magnetic fields, or the classical light beam and electromagnetic waves, they have their phase behavior as a result of the ensemble of a huge number of individual photons. If we block the lower path, we remove the interference of the electric field and wave function going to the detectors. This increases the probability and intensity reaching detector D1. It was 0 and now it is some. This happens both classically and for photons. But why did this work correctly for photons? It works because the way we treated the wave function was correct for photons. When we combined wave functions as linear superpositions of wave functions at the outputs of beam splitter 2, we added the wave functions, the probability amplitudes, with their correct phases. We did not add the probabilities. This handles wave function interference correctly. It's the phases that produce constructive and destructive interference, which then shows in the probabilities. Now, what happened to the photon at the beam splitters? This is a possible time to take a break. Here's what quantum mechanics says. Some of this is a repetition from lecture B6, but I think it's worth repeating because this is some of the most important phenomena of quantum mechanics. The photon did not split into two photons at beam splitter 1, and so it did not recombine two photons into one photon at beam splitter 2. Quantum mechanical phenomena are fundamentally probabilistic in nature. The wave function is the probability amplitude, and the square of its magnitude is the probability density or the probability. When a particle can take multiple paths or trajectories within a system or experiment, the particle's wave function or probability amplitude is a superposition or linear combination of the wave functions that would obtain for each possible definite path. The probability is the square of the magnitude of the wave function, the superposition wave function. Differences in phases in the superposition give rise to interference, constructive and destructive, as we see in the probabilities that we computed. It's wrong to say the photon took both paths. It would be better to say that the wave function is as if the photon could take either path with equal probability amplitude, and we don't know which path it did take. If we didn't measure which path was taken, top path, bottom path, or both, then we don't know it. And that's the end of that. We should not make a guess about which path it took. We should not try to apply human macroscopic world experience, reason, and logic to a quantum world measurable quantity that we did not measure. The fact that the probability distribution shows interference due to the wave function being a superposition due to the two paths, as if a single photon could possibly go through both paths, is very confusing for us to understand and believe, because we don't see anything like this in the real macroscopic world that we see and model from the time we're infants. So our brain builds our experience from the world around us, and these quantum effects are different than the entirety of our experience, reason, and logic about solid objects in the world. But all experiments verify this quantum reality and results. In general, when we do a measurement of a quantum system, the state of the system changes, randomizes after the measurement, except for a special case that we will talk about later in the course. For the Mach-Zehnder Interferometer, if we attempt to measure whether the photon or the particle definitely traverses the top path, the bottom path, or both paths, the which path measurement changes the system and the probabilities. For the changed system, we will get the single path result for the top path if the photon is detected transiting the top path. And likewise for the bottom path, we no longer get the double path interference that we get when we don't attempt to measure which path. This has been verified experimentally many times. This would be true even if we add instrumentation and measurement for which path, but we don't look at the results of which path got traversed. Just adding the mechanism to either path changes the system and the results. Detecting a photon removes and destroys that photon. Well, these quantum mechanical results are confusing and mysterious, but don't give up. With more experience, the confusion and mystery will reduce a little, but it'll never completely go away. The quantum world is mysterious. This is a possible time to take a break. Now, it turns out we can also do the Mach-Zehnder Interferometer with neutrons instead of photons using a single crystal neutral interferometer, and we get the same results. So our use of quantum mechanics is correct for the photon and for a neutron. Now, if you have a stronger mathematical background than I'm requiring so far, if you know complex numbers and vectors and matrices, and if you want a more general, abstract mathematical treatment of the Mach-Zehnder Interferometer than I gave, there are 2 lectures from the MIT Introductory Quantum Mechanics course, 804, by Professor Barton Zwiebach. Those 2 lectures are good and they're pretty accessible if you have a little more math background than we've used so far. And and they're short, and then you will have gotten a quantum mechanics lecture from MIT. Here's where those two MIT lectures are. Now, you would understand these a little better if you start from the beginning of the 804 lectures, and some of you have the mathematical background to do that. The MIT Introductory Quantum Mechanics course 804, it's excellent. It's accessible after my lectures if you know calculus and differential equations and have a college sophomore level of math and physics. I recommend, if you want to do this, I recommend that you take it on edX, either when it runs next or as an archive. Alternatively, you can watch the videos on MIT's OpenCourseWare here. This is the end of session B7.